In this video, the following topics will be covered: statistical and proximity-based methods, statistical approaches, and statistical data mining. Method 2, statistical methods. Statistical methods, also known as model-based method, which makes assumption of data normality. They assume that normal data objects are generated by a statistical model and the data not following the model are outliers. Detecting the model using a statistical model is the data points except for those in the region are as shown in the diagram are fit a Gaussian distribution where for a location x in the data space Gaussian distribution gives a probability density at x. Thus the Gaussian distribution can be used to model the normal data, that is most of the data points in the data set. For each object y in region R, we can estimate the Gaussian distribution of y, the probability that this point fits the Gaussian distribution. Because Gaussian distribution is very low, y is unlikely generated by the Gaussian model and this is an outlier. The effectiveness of statistical methods highly depends on whether the assumptions made for the statistical model hold true for the given data. There are many kinds of statistical methods. There are different alternatives to use various statistical methods. Examples are parametric and non-parametric. Effectiveness of proximity-based methods relies heavily on the proximity, the measure used. In some applications, such measures cannot be easily obtained. Moreover, proximity-based methods often have difficulty in detecting a group of outliers if the outliers are close to one another. There are two major types of proximity-based outlier detection, namely distance-based and density-based outlier detection. Clustering-based methods. Clustering-based method assume that the normal data objects belong to large and dense clusters, whereas outliers belong to small or sparse clusters or do not belong to any clusters. Detecting outlier using clustering, as shown in the figure, there are two clusters. Cluster C1 contains all the points in the dataset except for those in region R. Cluster C2 is very small, containing just 2 points in R. Cluster C1 is large in comparison to C2. Therefore, a clustering based method gives that the two objects in R are outliers. There are many clustering methods are available. Therefore, there are many clustering-based outlier detection methods also available. Clustering is an expensive data mining operation. A straightforward adaptation of clustering method for outlier detection is very costly and thus does not scale up well for large data sets. Statistical approaches. Statistical approaches assume that the objects in a data set are generated by a stochastic process. Uh, The general idea behind statistical methods for outlier detection is to learn generative model fitting the given data set and then identify those objects low probability regions of the model's outliers. However, there are many different ways to learn generative models. In general, statistical methods for outlier detection can be divided into two major categories: parametric methods and non-parametric methods. A parametric method assumes that the normal data objects are generated by a parametric distribution with a parameter. The probability density function of the parametric distribution f of x comma theta that gives the probability that object x is generated by the distribution. The smaller this value, the more likely x is an outlier. A non-parametric method does not assume a priori statistical model. Instead, a non-parametric method tries to determine the model from the input data. Note that the most non-parametric method do not assume that the model is completely parametric free. Instead, non-parametric methods often take the position that the number and nature of the parameters are flexible and not fixed in advance. Parametric methods 1. Detection of univariate outliers based on normal distribution. Suppose your city's average temperature values in a particular month in the last 10 years are given in value ascending order, right from 24.0 degree and 28.9 degree and so on up to 29.4 degrees Celsius. Let us assume that the average temperature follows a normal distribution, which is determined by two parameters, that mean, mu, and the standard deviation. We can use the maximum likelihood method to estimate the parameters mu and sigma. That is, we can maximize the log likelihood function that is given in the screen. Univariate outlier reduction, the Grubbs test. It's another statistical method under normal distribution. For each object X in a dataset, compute its z-score, where the value is taken by the t distribution at a significant level, alpha divided by 2n, and n is the number of objects in the dataset. Detects the outliers in univariate data. Assume the data comes from normal distribution. Detects one outlier at a time, remove the outlier and repeat. There is no outlier in the data. There is at least one outlier. Parametric methods to detection of multivariate outliers. Multivariate data, a data set involving two or more attributes or variables. Transform the multivariate outlier detection task into a univariate outlier detection problem. Method 1 is computing the Maglovis distance. Method 2 using the chi-square statistical distance. Method 1, compute the Maglovis distance. For a multivariate data set, let O dash be the mean vector for an object O in the data set. The Maglovis distance from O to O dash is given as MD distance of O comma O dash. It is given, it's shown on the screen, where S is the covariance matrix. So Maglovis distance is a univariate variable, and thus Grubbs test can be applied to this measure. Therefore, we can transform the multivariate outlier detection task as follows. First one, we can calculate the mean vector from the multivariate data set. Second, for each object, we can calculate the Maglovis distance. Third one, detect the outliers in the transformed univariate data set. The fourth one, if the Maglovis distance is determined to be an outlier, then O is regarded as an outlier as well. The next one is the multivariate outlier detection using the chi-square statistical. Chi-square statistics can also be used to capture the multivariate outliers under the assumption of normal distribution. For an object O, the chi-square statistics is given as shown in the screen. Chi-square equal to sigma I is equals to 1 to n, and OI minus EI whole square divided by the EI. Using a mixture of parametric distribution. If you assume that the data were generated by a normal distribution, this works well in many situations. However, this assumption may be overly simplified when the actual data distribution is complex. In such cases, we can assume that the data were generated by a mixed parametric distribution. Consider the data set as shown on the screen. There are two big clusters are available, C1 and C2. To assume that the data are generated by a normal distribution will not work well here. The estimated mean is located between the two clusters and not inside any cluster. The objects between the two clusters cannot be detected as outliers since they are close to the mean value. To overcome this problem, we can instead assume that the normal data objects are generated by multiple normal distribution, two in this case. That is, we assume two normal distributions for any object O in the data set. The probability O is generated by the mixture of the two distributions is given as per the formula given shown on the screen. All electronic records, the purchase amount for every customer transaction shown in the figure, which uses a histogram to graph these amounts as percentage given all transaction. For example, 60 percentage of the transaction amounts are between the $0.02 to and $1,000. We can use the histogram, a non-parametric statistical model, to capture the outliers. For example, a transaction in the amount $7,500 can be regarded as an outlier because only as per the formula given in the screen of transaction have an amount higher than the $5,000. On the other hand, transaction amount of $385 can be treated as a normal because it falls into the bin. Proximity-based approaches. Given a set of objects in feature space, a distance measure can be used to quantify the similarity between objects. Intuitively, objects that are far from others can be regarded as outliers. Proximity-based approaches assume that the proximity of an outlier object to its nearest neighbors significantly deviates from the proximity of the object to most of the other objects in the dataset. There are two types of proximity-based outlier reduction methods. Number one, distance-based and density-based methods. Distance-based outlier detection method concerns neighborhood of an object which is defined by a given radius. An object is then considered as an outlier if its neighborhood does not have enough other points. A density-based outlier detection method which investigates the density of an object and that of its neighbors. Here, an object is defined as an outlier if its density is relatively much lower than that of its neighbors. Distance-based approaches. A representative method of proximity-based outlier detection uses a concept of distance-based outliers. For a set D of data objects to be analyzed, a user can specify a distance threshold small r to define a reasonable neighborhood of an object. For each object O, we can examine the number of other objects in the R neighborhood of O. If most of the objects in dataset D are far from O, that is not in the R neighborhood of O, then O can be regarded as outlier. The basic assumptions are normal data objects have a dense neighborhood. Outliers are far apart from their neighbors, which have a less dense neighborhood. In the distance-based approach, how can we compute the distance-based r, pi of an outlier? A straightforward approach is to use nested loops to check the r neighborhood for every object as shown in the screen. For any object oi, 1 is less than I and less than or equal to n. We can calculate the distance between oi and the other object and count the number of objects in the neighborhood of oi so that we can find the pi, n. A straightforward nested loop approach takes O of n squared time. Surprisingly, the actual CPU runtime is often linear with respect to the dataset size. For most non-outlier objects, the inner loop terminates early when the number of outliers in the dataset is very small, which should be the case in most of the time. Correspondingly, only a small fraction of the dataset is examined. Distance-based approaches, we can exclude the point from further consideration if its neighborhood contains more than the distance-based number of points. The points need only compare with the points from neighboring cells. Compute the distance range join using spatial index structure. Build the grid also. Method. Cell is a grid-based method for distance-based outlier detection. In this method, the data space is partitioned into a multi-dimensional grid where each cell is a hypercube that has a diagonal length of r by 2, where r is a distance threshold parameter. In other words, if there are L dimensions, the length of each cell is r by 2 to the 2 into square root of T. Consider a two-dimensional data set, for example, as shown in the figure, shows a part of the grid. Length of each cell is r divided by 2 to the 2 into square root of 2. Consider the cell C as shown in the screen. The neighboring cells C can be divided into two groups. The cells immediately next to the capital C constitute the level 1 cells, and the cells 1 or 2 cells away from the capital C in any direction constitute the level 2 cells. The two levels of cells have the following properties. Level 1 cell property, given any possible point x of capital C and any possible point y in a level 1 cell, then distance of x comma y less than or equal to small r. Level 2 cell property is given any possible point x of capital C and any point y such that distance of x comma y greater than or equal to small r, then y is in a level 2 cell. Thus, we only need to check the objects that cannot be prone uneven for such an object O, only need to compute the distance between O and the objects in the level 2 cells. Based approaches. The general idea of the density based approaches are compare the density around a point with the density around its local neighbors. The relative density of a point compared to its neighbors is computed as an outlier score. Approaches essentially differ in how to estimate the density. Second, the basic assumption about the density-based approaches are the density around a normal data object is similar to the density around its neighbors. The density around an outlier is considerably different to the density around its neighbors. Distance-based outliers such as distance-based R, pi are outliers are just one type of outlier. Specifically, distance-based outlier detection takes a global view of the dataset. Such outliers can be regarded as global outliers for different reasons. Many real-world datasets demonstrate a more complex structure where objects may be considered outliers with respect to their local neighborhoods, rather than with respect to the global data distribution. Local outliers are outliers comparing to their local neighborhoods instead of global data distribution. As shown in the figure, O1 and O2 are local outliers to C1. O3 is a global outlier, but O4 is not an outlier. However, proximity-based clustering cannot find O1 and O2 are outliers. So the density around an outlier object is significantly different from the density around its neighbors. Methods are used to use the relative density of an object against its neighbors as the indicator of the degree of the object being outlier. K distance of an object, O, the distance of O is calculated. K distance neighborhood of O also calculated as Nk of O. Models have different problems with different densities. Compare the neighborhood of points from areas of different densities. Compare the density around a point with the density around its local neighbors. The relative density of a point compared to its neighbor is computed as an outlier score. Approaches also differ in how to estimate the density. The basic assumptions are the density around a normal data object is similar to the density around its neighbor. The local outlier factor is the average of the ratio of the local reachability density of O and those O dash is K nearest neighbors. The lower the local reachability density of O is smaller than the sum of Nk points. So, and the higher the local reachability density of the K nearest neighbors. The local outlier factor has some good properties for an object deep within a consistent cluster, such as the points in the center of the cluster C2 as shown in the diagram. The local outlier factor is close to 1. This property ensures that objects inside clusters, no matter whether the cluster is dense or sparse, will be mislabeled as outliers. The local reachability density of O and the higher the local reachability density of K in nearest neighbor of O, the higher local outlier factor. This captures a local outlier whose local density is relatively low comparing to the local density of its K nearest neighbor. The density-based approach, the model, the reachability density distance can be calculated. Reachability minus distance of Kp, comma O, that is, which introduces a smoothing factor also. Local reachability distance is of point P. As shown in the diagram, it is calculated. Local outlier factor also calculated. Local outlier factor equals to 1. The point is in a cluster a region with homogeneous density around the point and its neighbor. Then the local outlier factor is greater than 1. The point is an outlier. So choice of K, the min points, specifies the reference set. Originally implements a local approach and outputs a scoring of assigns a local outlier factor value to each point. Of local outlier factor, mining the top in local outliers. The idea is usually a user is only interested in the top in outlier. Do not compute the local outlier factor for all the data objects. Methods are used to compress the data points into microclusters using CF trees of bridge model. Derive the upper and lower bounds of the reachability distances. Then compute upper and lower bounds of local outlier factors values for microclusters and sort the results. Prune microclusters that cannot accommodate the points. Iteratively refine remaining microclusters and prune points accordingly. Of local outlier factors we continue. Connectivity based outlier factors are the motivations are in regions of low density, it may be hard to detect the outliers. Choose a low value for K is often not appropriate. The solution is treat the low density and isolation differently.